Let's give an example of applying of Euclidean algorithm on how to find greatest common divisor of two numbers. Example of Euclidean algorithm. For example, we want to find a greatest common divisor of numbers 525 and 231. What will be greatest common divisor of these two numbers? First of all, we know that number 525 can be represented as 231 times 2, and we will have a remainder 63. And since our remainder 63 is less than 231, we can continue our division, and 231 will be 63 3 times plus another number 42, and this number 42 is less than 63, and let's continue our algorithm. Continuing our algorithm, we will have that 63 is 42 one time plus remainder 21, and at last 42 is our remainder 21 times 2. And using our previous algorithm, we know that this number 21 will be greatest common divisor of 525 and 231, because at the first step we will have that greatest common divisor of these two numbers 525 and 231 is equal to greatest common divisor of 231 and 63, and this is equal to greatest common divisor of 63 and 42, and this is equal to 21. So our final number 21 is a greatest common divisor, and here we can write that greatest common divisor of 525 and 231 is 21. Next result, or theorem 4, we can write, assume we have two numbers am and bm. In this case, greatest common divisor of two numbers a times m and b times m is equal to greatest common divisor of a and b times this number m. So in our denotion of greatest common divisor, we can take this common factor m out of our greatest common divisor. How to prove this equality? This is actually quite easy. To easily understand this equality, we have to look at Euclidean algorithm. Let's look at Euclidean algorithm again. And if we look at our algorithm, Euclidean algorithm, we will see that greatest common divisor of AB is equal to greatest common divisor, or GCD, of B and R2, and this is equal to greatest common divisor of R2 and R3, and so on, and this is equal to Rn. Let's rewrite these equalities, and we will have greatest common divisor of A and B is equal to greatest common divisor of B and what was this? R2, B and R2, which is equal to greatest common divisor of R2 and R3, and so on, and which is equal to greatest common divisor of Rn minus 1 and Rn, and this is equal to, at last, equal to Rn. In these equalities, we can multiply each element of this equality by m, and which proves our result. And of course, from these two elements of our equality, we can see that greatest common divisor of, once again, this is equal to this, and this number is this number. I hope this is quite clear, and that's why we can take common factor m out of greatest common divisor, and greatest common divisor of am and bm is equal to greatest common divisor of ab times m. Next theorem, theorem number 5 in our section, we can write, assume we have delta is a common divisor, or CD, of two numbers a and b. In this case, a divided by delta and b divided by delta. Since delta is a divisor of a and b, these two fractions are integers, and greatest common divisor of these two numbers will be equal to greatest common divisor of A and B divided by delta. How to prove this result? This is actually quite obvious because greatest common divisor A and B can be written as A divided by delta times delta, and B can be written as B over delta times delta. And we can, using previous result, can take this delta, we can take it out, and we will have A divided by delta, and here B divided by delta, times delta. And using this result, if we divide both sides, in particular these two parts, we divide by delta, we will have A, greatest common divisor of A and B divided by delta, is equal to A, greatest common divisor of A over delta and B over delta. And this is our result we wanted to prove. In particular, if delta is not common divisor, but greatest common divisor of our two numbers, A and B, here, this delta will be equal to greatest common divisor of A and B, and all of this fraction will be equal to 1. And we can write A divided by greatest common divisor of A and B, and B divided by greatest common divisor of A and B, and greatest common divisor of these two numbers will be equal to 1. That's all. Our next result is if A and B are relatively prime, or we call it also coprime. In this case, greatest common divisor, AC and B, since these two numbers, A and B, are relatively prime or coprime, is equal to greatest common divisor of C and B. This is quite obvious formulation, but in number theory, we very often have problems with very easy formulation, but to prove this problem can be very tricky and hard. To prove this result, we have to show that first, to one side, we have to show that greatest common divisor of AC and B divides greatest common divisor of C and B. And to the opposite side, we have to show that greatest common divisor of C and B divides greatest common divisor of AC and B. And of course, if this number divides this number, and opposite, this number divides this number, these two numbers are the same numbers. And we will prove this. Okay, let's begin. First of all, we have that AC, B, the greatest common divisor of AC and B, divides, let's write it, divides, by definition, greatest common divisor of AC and B divides AC and divides B. It divides AC and B. And since it divides B, it also divides BC. Okay? Next, since our number, this is greatest common divisor of two numbers, this is number, since this number divides two numbers, we know from previous result that if we have two numbers, then divisors, set of divisors of these two numbers, and GCD, greatest common divisor of these two numbers, coincide. That's why if this number divides these two numbers, this number have to divide GCD of these two numbers. That's why this our number, GCD of AC and B, divides GCD of these two numbers, AC and BC. And since it divides this number from another side is equal to AB, GCD of AB times C. But GCD of AB is 1. That's why this is C. So in other words, AC and B, GCD of AC and B divides C. So it divides C. And we know by definition that it also divides B. And since it divides C and B, it also must divide GCD of these two numbers, of C and B. So we proved our result to one side. That's why this our number, GCD of A, C, and B, divides GCD of C and B. Let's further prove that opposite result, that GCD of CB divides GCD of A, C, and B. And that's why, in this case, these two numbers will be equal. Let's prove opposite result. We have to prove that GCD of C and B divides GCD of A, C, and B. Obviously, GCD of C and B, by definition, since this is greatest common divisor of C and B, it have to divide C and B. And since it divides two numbers, C and B, it has to divide these two numbers, AC and B. And since it divides these two numbers, AC and B, it has to divide GCD of these two numbers. That's all. So we have our result. The proof is over. And that's why these two numbers coincide. Once again, if we have A and B co-prime or relatively prime, in this case, GCD of two numbers of AC and B, since these two numbers A and B are co-prime, is equal to greatest common divisor of C and B.